Let me share my screen. All right, so here we have it. Or does anybody have any particular questions before we begin? From anything, from the homework? Again, this is your time. This is a review session, so let's review. Number 3, Natalia, from what section? Number 3 in quadratic functions, or number 3 on finding polynomials from a graph. Okay. Finding polynomials from a graph. Oh, this one. All right, so I'm gonna circle this one. Okay, so I want to go over how to do this. So we have a polynomial function with degree 4, okay? And we have the graph. So what's important to figure out? First of all, they give us information that the polynomial has to be degree 4. So that's one piece of information. And then from the graph, what can I get from the graph? So what information does the graph give me? It is positive. Well, yeah, it is mostly positive. But the more important ones are the following. The number 1 is what are the x-intercepts? Remember, the x-intercepts are also known as the roots. So what are the x-intercepts or the roots according to the graph? Well, according to the graph, where does it touch the x-axis? At 1 and at -2. So that's important, because once I have x equals -2 and 1 as the solutions, then I can figure out immediately from here, I can find out what are called the factors. What are the factors of my polynomial? Remember this? So if x equals -2 is a root or a solution, then x plus 2 is a factor, and x minus 1 is another factor. Do you see that? So that's the first thing we need. This is what we need, the factors of p of x. The factors of p of x comes from the graph itself. The second piece of information that I can figure out are the y-intercepts. The y-intercept. The y-intercept is when it crosses the y-axis, of course, and it crosses it at 4. So when x equals 0, y equals 4. Okay. So we know the fact that the factors are given by the x-intercepts, or the solutions, or the roots of the graph, of the function. We're able to figure out the y-intercept. And then the last thing we have to always note and be able to identify is what's called the end behavior. And the end behavior is the kind where they both behave the same way at the ends. So as x goes to infinity, y goes to infinity. As x goes to negative infinity, y goes to positive infinity. Okay, so I'm going to continue over down here. You know what? Let me change this to a white color. Oops. Try that. Okay. So then what? Then we know that the p of x, what do we know about p of x? P of x has this form. We have a leading coefficient, not sure what it is yet. We call it A. We have an x plus 2, and we have an x minus 1. One thing that we haven't discussed, we haven't touched upon yet, is that the degree has to equal 4. Right now, the degree equals what? Is the degree equal to 4 in this particular polynomial? Like if I were to multiply all the x's out, right? It's not, right? The highest power would be what? X squared. But we want the degree to be 4. And not only that, if you notice, at the x-intercepts, this is a situation where what? The graph doesn't cross the x-axis, it just bounces back. Remember what must it mean for a graph to bounce back at the x value that it intersects, that it touches on the x-axis? It means that the multiplicity is even, which means that the power associated with the factor must be even. In this case, the exponent here is an odd exponent, so this can't be true. So then what must be true is that this must be a 2 squared, and this must be also a squared. So do you guys see that? So this 2 and this 2 is because the graph of P of x bounces back. Sorry, I should put this in quotations. Bounces back at the x-intercepts. Which means their multiplicity is even. And the multiplicity refers to the power of the factor, or the exponent of the factor. Everybody with me so far? So far, this is what I have. So far, that's my polynomial. And then finally, to find what the a value is, to find this, I must use the y-intercept information. So what's the y-intercept information? Well, if I plug in 0, I get a times 0 plus 2 squared times 0 minus 1 squared. The result should give me 4. 0 plus 2 squared is 2. 2 squared is 4. 0 minus 1 is, 0 minus 1 is negative 1. Negative 1 squared is positive 1. So you get 4a equals 4. So then a equals 1 in this case. So then what's my final answer? My final answer is that P of x equals x plus 2 squared times x minus 1 squared. And that is my final answer. Any questions? Any comments about how to find the the equation of a graph? How do you know it's the fourth degree? Well, it tells me. It says write a polynomial function with degree 4. So that information I don't make up. That's what's given to me from the problem itself. Okay, any other questions about this? Does this seem reasonable? Everything we've done, x-intercepts. We know the x-intercepts by looking at the graph. We find the factors. The y-intercept by looking at the graph. And behavior by looking at the graph. Then we utilize the fact that the factors make up the polynomial. Then we have to figure out what are the certain, what's the correct exponents for each factor given the graph and given the degree of the polynomial. And we find the a value, the leading coefficient, by plugging in the y-intercept. And we get the final answer. And if you want, you can check it for yourself. You can graph this, and if it graphs, and if it looks just like this, going through these points here, exactly like we've done, like we see it here, then it's the correct answer. All right, so that's number 3. If there's no other questions for this, we can go on to the next one. I think Jaskirat says number 2 from polynomials. So number 2, which yeah, so which number 2, Jaskirat, are you referring to? Because there's several number 2s under this one. Are you talking about end behavior, graphing polynomials? Oh, end behavior. Okay. So end behavior should be a little quick one. So how do we find the end behavior? Remember, end behavior comes from what? It comes from the knowing the degree of the polynomial and knowing the sign of the leading coefficient. That's all you need to know. So the degree of this polynomial, the degree of g, is what? It's 6, which means that it's what? Even. So it's an even degree polynomial. That's the first thing. The second thing is, what about the leading coefficient of g of x? What's the leading coefficient? The leading coefficient is 1/2, which means it's what? Positive. These are the only things I care about. It has a positive leading coefficient and an even degree. So that means that this polynomial looks like the only, remember we have like the 4 basic polynomials? One of the first ones is x squared, has an even degree and a positive leading coefficient. So at the end, it looks like this, at the ends. Sure, in inside here, there might be something, some kind of ups and loops and ups and downs. I mean, not loops, but like some rise and some fall in between, and there might be, but at the ends, that's what it looks like. It looks like it's just pointing upward from either direction. So the end behavior for this polynomial is 1 as x goes to infinity, y goes to infinity, and 2 as x goes to negative infinity, y goes to positive infinity as well. Okay? And that would be it. This is my end behavior for g of x. All right? Any questions about that? So again, it's all about the degree, and it's all about the leading coefficient. If you know those those pieces of information, then you can be able to figure out the end behavior. And there's only 4 scenarios that you have to consider. Okay, so that's end behavior. So we've done end behavior. We've done finding a polynomial from a graph. What else, guys? What else do you have in mind here? Sihan wants to do graphing exponential equations. And yes. So here we have, so which one would you like to do? We have a lot to choose from. We got 7. So anyone? Number 7? Okay. Number 7. So let's look at number 7. So what we have here is f of x equals e to the x minus 3 plus 4. So the first thing I want to figure out in part A is the parent function, of course. Hold on. It's the parent function. So what is my parent function? So what's the most basic kind of exponential function whose base is e? Remember, parent functions look like, and for exponential functions, they look like this. Y equals a times b to the x. Or you can just say y equals, actually, y equals b to the x. That's the form of the parent function for any exponential function. And Andrew, that's right. The parent function should be e to the x, because that's where you're like that's like where you start from. That's your base. And then we realized, but f of x is not just e to the x, it's a transformation of e to the x. So we have to figure out what are the transformations that are applied. What are the transformations? Does anybody see that? So we got -3 next to the x, and we got a +4 in front and outside of the function. So what do these things here indicate to me? What kind of transformations are being applied? What does this do? And what does this do? It's a horizontal shift right and a vertical shift up. Very good, Tiffany. That's right. So then the first one is a horizontal shift to the right by 3 units. And then number 2, it's a vertical shift upward by 4. So far, so good. And then part C. Part C asks what? It asks for the asymptote. What kind of asymptote do I have? Remember, the asymptote comes from the fact that it's a vertical shift up. So what kind of asymptote is this new function have? X equals 4? Not quite. X equals 4 is a vertical asymptote. What kind of asymptotes do exponential functions have? They don't have vertical. They have horizontal. So this asymptote for exponential functions is horizontal. So to y equals 4. And remember, the asymptote horizontally, no, it's not a slant. It's a horizontal asymptote. The horizontal asymptote is associated with the vertical shift. So then it says, what's the graph, right? The domain and range. We just want the domain and range. Okay, so what would help first before we continue is graphing it or giving a sketch. Okay, so remember we utilize the parent function graph first, and everything we know about the parent function. It's e to the x, and it's exponential growth function. So it's gonna look something like this. It's gonna get really close to 0, and then it skyrockets up. It skyrockets. So this is y equals e to the x. We know everything about e to the x. We should already know that the domain is all real numbers. The range is from 0 to infinity. And the horizontal asymptote is y equals 0. But then what do we do to this function? It's horizontal asymptotes for most, yeah. I would say it's for all exponential functions. Every exponential function has a horizontal asymptote. And only in a horizontal asymptote. There is no vertical asymptotes. Vertical asymptotes only are for logarithmic functions, which are the inverses of the exponential functions. So that's how they're related. And then what happens? You shift this graph. Whatever this graph is, you shift it over by 3. You shift it over by 3. So let me use a different color. So if I shift it by 3, still have the asymptote being the same thing. It's just that now this is going to be 1, 2, 3, right? I'm going to be crossing it like this. Of course, this is not the greatest sketch of this. And this here is y equals e to the x minus 3. So I'm shifting it over by 3. And then what happens to this guy? Why is the asymptote 4? We'll see him. I'm going to try to explain it at this very second. The reason why it's 4 is because we start with a parent function. We start with our parent function whose asymptote is y equals 0. That's what we start with. So y equals 0 is a asymptote for this function here. But what do I do to this function? I shift it over by 3 units to the right. If I shift it over by 3 units to the right, horizontally speaking, the asymptote remains y equals 0. But then when I apply the second transformation to this guy, I shift everything up by 4. And when I mean everything, I mean everything. Every y value goes up by 4. So this y value that's originally y equals 0 is now added by 4. So that is why I'm just gonna draw this in a different graph, because then it's gonna get a little too messy. So let me put this here. So then I'm just gonna put this at 1, 2, 3, right? So again, this is my original. This is my my graph with only the x minus 3, with only the shift to the right by 3. But then I'm gonna move everything by 4. So this here 3. This point here should be shifted up by 4. So this is 4 right here. So I'm shifting everything up by 4. This will be shifted up by 4 a little bit. So somewhere, let me see. Whoa, 1. Sorry, this is not by 4. Right here, boom, 1. And then you have something here. And y equals 4 is a horizontal asymptote. So this is y equals 4. So I'm going to have a graph that looks like this. So this is my graph. Y equals e, or I should say graph of g of x. Just write graph of g of x. And so then from here, what's the domain and range in part D? So the domain for this exponential function, as you can tell, hasn't been changed. Even if I shift it to the left or to the right, or if I shift it up or down, the domain still remains negative infinity to positive infinity. And then what's the range? The range is everything above the asymptote. So it's going to be from 4 to positive infinity. And there we have it. So this is what's expected of you, being able to look at a function, whether it be logarithmic or exponential, find the parent function, know what the transformations are, identify the asymptotes, identify the domain and range, and give a rough sketch. Of course, not going to be perfect because exponential functions can get a little bit crazy as it gets to the ends, because this goes really high up and this gets really close to the asymptote. But besides that, as long as you have one of the points here that's correct, which comes from the parent function point that has to go through the point 0, 1, then you can just apply the transformations to this point to figure out what's the final point, and which in this case would be 3, 4. All right, so any questions about this problem? Okay, if no other questions, let's move on. So Chen says coterminal angles number 4. Okay. So I want to know about coterminal angles. Number 4. So negative 5 pi over 3. I want an angle to be coterminal to this. Now, coterminal angles, remember we discussed, are angles that refer to the same terminal side. In order to refer to the same terminal side, you have to add by 360 degrees to get the next one, or you have to subtract by 360 degrees to get the next one. And you can add and subtract by 360 degrees as many times as you'd like. In this problem, we want to go, this is in radians, okay? So we want to go from radians, negative 5 pi over 3, and go find a coterminal angle to this. And the coterminal angle must be between 0 and 2 pi radians. So right now I'm in negative 5 pi over 3. So I am nowhere close to 0 to 2 pi radians. So what I must do, since this is negative, I must add by 2 pi and see where does it lead me. Will it keep me being negative, or will I break the negative and go on to the positive values? So if I add this, how do you add two fractions? Right? Because this is, you can write this as a fraction. So I must have the same denominator. So this must mean that I must add this by what? 6 pi over 3. Same denominator is 3. Negative 5 pi plus 6 pi is 1 pi. So pi over 3 is a coterminal angle to negative 5 pi over 3. If you want to have a bit more reasoning to this, think about the graph. And remember pi over 3? Remember we talked about pi over 3? We talked about it being, you have to divide up. It's like dividing up pi here. This is pi, right? It's like dividing this up into 3 equal parts. Something like this. So this is pi over 3. This is 2 pi over 3. This is 3 pi over 3. This is 4 pi over 3. And then this is 5 pi over 3. And this is 6 pi over 3 when you come back, which is 2 pi. Okay, and remember, we're going in the positive direction in this manner. But if we go in this manner, this is negative. So this is equal to what? Negative pi over 3. It's like saying this is the first cut in the negative direction. And then this is going to be the second cut in the negative direction. This is the third cut in the negative direction. This will be the fourth cut in the negative direction. And this would be the fifth cut in the negative direction. So there you have it. You got two angles that are coterminal. One of them goes this way. So pi over 3 goes this way. Look, pi over 3 is this. That's this angle, pi over 3. But then if you go the other way, this is negative 5 pi over 3. But do you see how they're coterminal? Because they are on the same terminal side. So that's how you do this coterminal angle stuff. Any questions about this? All right, next. Anything else? What's next? Yes, this will be. Can you do one more of the coterminal? Yeah. So which one do you want to do? Do you want to do another radian one or a degree? Yeah, all you have to do is get it in between the angle 0 and 360. If it's degree, or if it's a radian, it has to be between 0 and 2 pi. So let's look at the other radian one, since people have less familiarity with the radians. So here we have 19 pi over 6. So 19 pi over 6, right? I think it would be helpful to have this in mind, this kind of graph again that we have created. And in this case, we have pi over 6, right? Our pi is divided into 6 equal slices. So we have one slice, pi over 6. We have another slice, 2 pi over 6, which is equal to pi over 3. We get the third slice, 3 pi over 6, which is pi over 3, pi over 2. And then we have the fourth slice. It's 4 pi over 6. And then we have the fifth slice, 5 pi over 6. And remember, pi over 6 is equal to 30 degrees. So we're taking 180 and dividing it into 6 equal parts, so that's 30 degrees. And then we continue with this. And we keep on dividing it up into thirds. So this is 7 pi over 6. This is 8 pi over 6, which is equal to 4 pi over 3. This is 9 pi over 6. This is 10 pi over 6. This is 11 pi over 6. And this is finally 12 pi over 6, which is equal to 2 pi. Do you see that? And then so that's when you go around once. You go around once. But you already see I have 12 pi over 6 already. And look what I'm trying to look at. 19 pi over 6. So this is 12 pi over 6. So then if I go around once, this is 12 pi over 6, which is 2 pi. And then if I continue going around after the first revolution, this will no longer be pi over 6. This will be the same thing as saying what? 13 pi over 6. Do you see that? That's coterminal. And then this one here would be what? 14 pi over 6. I keep on going. This is going to be what? 15 pi over 6. This is going to be what? 16 pi over 6. This is going to be what? 17 pi over 6. This is going to be what? 18 pi over 6, right? And this will be finally 19 pi over 6. So 19 pi over 6 refers to the angle that goes what? It goes around once and then comes back down like this. This is 19 pi over 6. And all we want is the angle that's associated with the same thing, but that's less than 1 revolution around. And that happens to be this angle here. You see that? They're both on the same terminal side. It's just that one of them, you go less than 1 revolution around. The other one, you had to go 1 revolution and go all the way around again. And let's say you didn't have this visual representation. What you would do is think about what happens if you either add or subtract by 2 pi 2 pi radians. So in this case, you would have to subtract because 19 pi over 6 is bigger than 2 pi. It's bigger. So you have to subtract and see what happens. And you get 19 pi over 6 minus, and then this becomes 12 pi over 6. Again, you see that? We have that here already. And then when you subtract, you get 7 pi over 6, which is exactly the coterminal angle. So that's how you do it. And eventually, this will be embedded in your head, eventually. For now, cutting this up, hopefully you start to see the visual connection to the angles and radians. Okay, so that's 2 and 4 for coterminal angles. What else? Degrees to radians, part 5. Oh, pardon me, radians to degrees. So radians to degrees. So we have this last one here. So we have radians to degrees. So the radians to degrees one here is negative 7 pi over 12. So my my radian measure is 7 pi over 12, negative 7 pi over 12. And I want to go from radians to degrees. So what must I multiply by? I must multiply by 180 over pi. And when I multiply, I can cross cancel the pi's out. Those pi's go away. And then 12 goes into 180 how many times? 12 goes into 180. Does anybody know? So it divides it, right? 15. So we get 15 here, and this is 1. So negative 7 times 15 is what? So you're multiplying 15 by 7, and you get negative 1. You get negative 105. That's right. So that's it. The degree measure of the degree measure of negative 7 pi over 12 radians is negative 105 degrees. And that's the extent of this. So this part here shouldn't be too bad. Like this last part, even though coterminal angles might be a little tricky, the radians and degrees to radians, you're just multiplying by a particular factor. So if you go from radians to degrees, you multiply by 180 over pi. And if you're going from degrees to radians, you're multiplying by pi over 180. Okay, anything else? So is that good angle measure? We got logs here as well. We got rational functions. The graphs of that. Now that's pretty good. Good stuff. Synthetic division, quadratic modeling. So can you do logs? Yeah. So what part of logs? So we have a lot in logs. We can fill out the table. Solving, yeah. I mean, we could, yeah, I love equations as well. But yeah, I think you meant to say solve, right? So solving equations. So right here. Number 2. Number 2, right? But which part of number 2? A. All right. So let's look at this one. So we have a logarithmic equation, and I want to solve it. Okay, so let's do that. So we have 2a. 2a says 2 log of x equals log of 2 plus log of 3x minus 4. Okay. Yeah. So how do we begin? Or what's the goal here? The goal has never changed much, right? When we solve, we want to solve for x. Okay. I want to know what x equals. Problem is I have these log expressions here. So the first approach that we should have with these is to make the logs into a single expression, a single logarithm. So for example, on the right side, I got 2 logs here, log 2 and log 3x minus 4, and it's a plus in between. I can put them together if I were to do what? I would apply the sum rule, right? So that means that I need to multiply log of 2 and multiply that with the thing inside the 3x minus 4. Do you see that? So I put them together. So basically for solving logarithms, you need to condense or make into a single log expression as much as possible. On the left side, for example, you have a 2, right? And this 2 here can be placed in the exponent here. So this becomes now log of x squared. Now look what you have here. You have log of x squared equals log of 3x minus 4. How do you get rid of the logs? To get rid of logs, you need to do the inverse function. What's the inverse function of log? It's exponentiating. So if you're talking about logarithm, right? Remember when we talk about log, y equals log of x, call it a function. Then the inverse of that function is what? 10 to the x. And what do you know about applying a function to the inverse or the inverse to the function? They cancel each other out. So this is when you quote unquote exponentiate. Exponentiate. You take 10 and raise it to that power, 10 and raise it to that power, and it cancels out, and it becomes x squared equals 2 times 3x minus 4. You can think of it that way, or you can think of it as I have the identical functions. They're identical because of equals. This is the same as this, which means that the input must also be the same because log is a one-to-one function. So the input, since the functions are the same, the inputs must be the same. So either way you interpret it, what happens is at the end you get x squared equals 2 multiplied by 3x minus 4. So what do you have now? This is 6x minus 8, x squared. This is x squared minus 6x plus 8 equals 0. And I have a quadratic. I have a quadratic equation. Can I solve this quadratic equation? Well, I can't factor it, right? Because there's nothing that multiplies to 4. Well, actually there is. What multiplies to 8 that gives me negative 6 when you add them? It's x minus 4 and x minus 2, right? So I get two possible solutions, but you have to be careful. So x equals 4 and x equals 2. But you always want to check. You always want to check. And we're going to check with the original equation. So x equals 4. What do we have? We have 2 times log of 4. Does this equal log of 2 plus log of 3 times 2 minus 4? And this equals what? Log of 2 plus log of 3 times 2 is 6 minus 4 is log of 2. And then this equals what? Log of 4. And sorry, this should have been 4. 4. 3 times 4. That's 12 minus 4 is 8. Pardon me for that. And then if you combine them, you get log of 16. And then on the left side, you put the 2 in front, and you get log of 4 squared, which is also log of 16. So this is good. So x equals 4 is a solution. Now let's try the other one. When x equals 2, is this a solution? So we get what? We get 2 times log of 2. Does this equal log of 2 plus log of 3 times 2 minus 4? 3 times 2 is 6 minus 4 is 2. So I get log of 2 plus log of 2. Does this equal 2 times log of 2? And yes, it does, because you're taking log of 2 and adding it not to itself. So of course this will be 2 times log of 2. I'm taking 2 logs of 2's. And I'm done. That's I could have specify that I can confirm that is also true. So we have two solutions. So my solutions to my equation or my solution, is x is equal to the set 2, 4. Okay? All right. Anything else? Natalia, of course. Okay, the review does not always only specify the review to the review sheet. Again, the review sheet is also limited. The review sheet, as you can tell, has a finite number, a limited number of questions for each topic, and maybe the ones that you have on the review sheet are not enough. Maybe you need more. So, of course, anything, any other question. So, which question are you referring to? Number 31 from the previous homework. So this is homework what? Homework number 7. Of course, any homework, anything. So number 31. Yeah, let me just give me 1 second, guys. I have to log into the sign. So number 31. Wow, that looks like a lot. So again, I have different numbers, okay? So this is number 31 from homework number 7. Logs, right? So this is 1/5 log x plus 3 to the 5th plus 1/3 parentheses log x to the 6th minus log x squared minus x minus 12 cubed. Looks crazy, right? So what I want to do is to combine it into a single log. So I need to take everything step by step. Okay. So when I say log of x plus 3, so let's look at this one first. What can we do to make this into a single logarithm? Well, the only thing I can think about is this 1/5 is in front of the log. So I can put the 1/5 and put it as a power. So I'm gonna have this as log. So let me just highlight that for you. So 1/5 here. I'm gonna put this as a power here. So this is log of x plus 3. X plus 3 is already to the 5th power. But what I'm gonna do now is raise it to the 1/5 power. Or you can put the 5 in front. That's right, Jen. Or you can do that. The whole point is what? What's 5 times the 5th? When you multiply the powers, 5 times the 5th is 1. So what are you left with? You're left with just log of x plus 3. So this 5 here, this 1/5 and the 5, they go away. They cancel out. Nice. Okay. The next thing is look at the expression in the brackets. So what about those brackets? What can I do with those brackets there? One thing I could do is distribute the 1/3. I could do that. So if I do that, what happens? I get log of x to the 6 minus 1/3 log of x squared minus x minus 12 cubed. And then what else can I say? This 1/3, I'm going to place it in front as an exponent. This 1/3, I'm going to put it in front, and not in front, but I'm going to put it in as an exponent inside. of the log. So this becomes log of x to the 6, and this is raised to the 1/3 power, minus log of x squared minus x minus 12 cubed, and all of this is being raised to the 1/3 power. And then what happens with the powers? Well, the 3 times 1/3, 3 times a third is 1. This equals 1. So this becomes just minus log of x squared minus x minus 12. And there's no more 3. There's no more 3 as an exponent. What's 6 times a third? It's 2, right? So we get log of x squared plus log of x plus 3. So I think the confusing thing behind all of this is the parentheses. The parentheses might seem confusing because it just appears out of nowhere sometimes. Now we're almost there. Now we can do what? Combine these logs here. This becomes, now look at the parentheses that I have. So I put inside the parentheses. So these parentheses are not the same as the parentheses that you'll see later. These parentheses indicate like a function. This is the input of log. And then the other parentheses is more of a multiplicative parentheses. So you're saying x plus 3, the parentheses multiplied by x squared. You see that? So these parentheses here, I just want to make sure it's slightly different than these parentheses, even though they're the same symbol. But when you interpret it, when you look at it, it's different. These indicate you're plugging this guy in to the function called log. And these parentheses here indicate that you could distribute. You see the difference? I'm not able to distribute this. I'm not doing that because that makes no sense because these parentheses don't tell me that. Okay? And then this is minus log of parentheses x squared minus x minus 12. And now because this is a minus, right? What does that mean? That means that you can take now x plus 3, multiply it by x squared, and divide that by x squared minus x minus 12. I can do the quotient rule. And then I'm like, you know what? I'm done. I did it into a single log. I was able to go from this whole thing here into a single log. But can you simplify always simplify? So always see if you can simplify. Can you simplify this expression here? And if you notice, you have a quadratic. The quadratic there looks factorable. So can I factor the quadratic in the denominator? I can. So what multiplies to negative 12 but add to negative x? Negative 1. Three and 4. Which one is negative? Which one's positive? So one has to be negative, one has to be positive. So x plus 3, x minus 4. Good. And now look what happens. See ya later. And this becomes, what does this become? This becomes log of x squared divided by x minus 4. And you see that? So we went from that whole expression here to a very simple one, which is equivalent. This is a good question. So again, it's all about knowing how to apply the laws of logarithms. Those 3 laws that we discussed: the product rule, the quotient rule, and the power rule. Okay, anything else? What else? What else? What else? Exponential and logarithmic equations. Yep, I'm there. So we have several equations. We've only done one. So which one of the other 9 should we look at? 1e? Okay. So 1e. So what is 1e? 1e says this. We got x squared e to the x plus e to the x, x times e to the x minus e to the x equals 0. Okay, this looks complicated, but it's really not as complicated as you might think. First of all, what's in every term? What expression is in every term? E to the x. So if e to the x is in every term, it kind of makes sense to factor it out because it's in every term. So if I factor out, I get e to the x multiplied by x squared plus x minus 1 equals 0. So then from here, I can say what? I got two different equations. Either e to the x equals 0, or I got x squared plus x minus 1 equals 0. Now, can e to the x ever be 0? Well, let's see if we try to solve for it. What if we try to solve for x? What would we have to do? Apply ln on both sides, right? That's how you would start this. But what's the problem when you do ln of x? So x equals ln of 0. If you put this in your calculator, what happens? You put this in your calculator, you get what? Undefined. No, this doesn't work, guys. There is no solution. There's no solution. So this actually has no solution for e to the x equal to 0. So all we really have left is a quadratic again. You see, these quadratics don't stop coming. They keep on coming. So this is a quadratic equation. I need to solve for it. Can I solve for this? Can I factor this, first of all? Is it possible to solve this by factoring? There are no two numbers, right? That multiply a -1 but add to +1. So the only thing we could do is a quadratic formula. So the quadratic formula is what? X equals -1 plus or minus the square root of 1 squared minus 4 times 1 times -1 all over 2. And x equals -1 plus or minus the square root of 1 plus 4 over 2, which equals -1 plus or minus the square root of 5 over 2. So I got two solutions. My two solutions are -1 plus rad 5 over 2 and -1 minus rad 5 over 2. And of course, you can check it out for yourself that those two x values work by plugging it back into the original equation. So that's how you solve it. All right. Okay, next. Expanding logarithmic expressions. Number 1. So number 1, I think I can do it right in here. Number 1, the first thing is I can rewrite the radical. I can rewrite the radical as raising it to the 1/2 power. So this is really ln of AB raised to the 1/2 power. And that 1/2, I can place it in front. So this becomes 1/2 ln of A times B. But a times b indicates that I can separate that even more. And this becomes 1/2, and make sure you put the parentheses or bracket. It's ln of a plus ln of b. And then if you'd like, you can also distribute that 1/2. So the final answer would be 1/2 ln of a plus 1/2 ln of b. And so now I have fully expanded it as much as possible. And that's number 1. Okay, for expanding logarithmic expressions. All right, anything else? Graphing exponential functions. Graphing it at number 4, okay. So let's look at number 4. So we got h of x equals 3 minus 10 to the x plus 1. So part A, parent function. What is the parent function? So remember, the parent function has this form, y equals 10 to the x. I mean, I just gave it to you, b to the x. So then the parent function would have to be y equals 10 to the x, right? That's the basic one. And it's just good to draw it out and to have like everything that you need to know for this. So we need to know that it crosses the y-axis at 1. It has a what? This is y equals 10 to the x. It has my domain being negative infinity to infinity. It has my range being what? Above 0. And it has the horizontal asymptote being what? Y equals 0. So this is all these are all the facts for the parent function. So I know that, and I'm going to use that for I'm going to use that for later. So I have parent function done. Sequence of transformations. So what are the transformations that I'm applying? So this is where things get interesting. So then I have three sequences, right? I mean transformations. So what do I have? What's being applied to 10 to the x? I have this plus 1 in there somehow. I got this negative as well. So what does that negative tell us? So there's a vertical shift upwards by 3. That's right. Usually we leave that to the end. So that's a vertical shift up by 3. I moved to the left by 1. That's right. So it's a horizontal shift to the left by 1. And I do have a reflection because that negative in front of 10. But what kind of reflection is it? Is it horizontal or vertical? Is it across the y-axis or across the x-axis? So it is a reflection. A reflection across what? Across the x-axis. Good. So I identified all the transformations that I'm going to apply to the parent function. So why don't we do that first? Okay, so I'm gonna wait. So I'm gonna start with this one. This is the first one. This is like my base case, or this is my parent function case. Okay, and then I'm gonna go this play by play. I'm gonna do a play by play here. So here we have a graph. I'm gonna copy this. Okay, so then what's the first thing I do? I reflect across the x-axis. And what am I reflecting? I'm reflecting the parent function. So I'm gonna have something at -1 instead that crosses the y-axis. I have this, look. So that's y equals -10 to the x. And then I'm gonna take this guy and I'm gonna shift it over to the left by 1. So then what's that point that I care about? The point that I care about is this one here. This is what? 0, 1. And then this became what? 0, -1. Then I shifted to the left over by 1. So this is my new point. -1, -1. And I still have something that looks like this. You see that? So this is going to be what? Y equals -10 to the x plus 1. But so far, has the domain changed? So far, the domain has stayed intact. And has the range changed? No, the range has stayed also intact. Well, actually, no. What happens to the range? What happens to the y values here? Since all the y values now have become negative, this is 0. Actually, no. This is -infinity to 0. That's my range. The range has changed. Has the horizontal asymptote changed? No, it hasn't. It's still going to be y equals 0. When I shifted this over to the left by 1, did I change anything here? It actually hasn't. That has stayed identical. Boom. And then one last thing is what? Shift up by 3. So this point, -1, 1, shifts up by 3. So I go 1, 2, 3. So I'm right here. Boom. This is going to be -1, -2. So then what has changed though? What has changed in this case? This is y is x. This is y, this is x. This is y, this is x. Now it has changed to +2, hasn't it? Pardon me, this should be positive. Actually, it's not +2. Pardon me. Oh, that's what you meant to say, right, Chet? +2. That's right. It is +2. But everything has shifted up by 3. So let me just be mindful of what's being applied here. So this is a reflection across x-axis. This is a horizontal shift by 1 to the left. And then we're gonna do the full thing is -10x plus 1 plus 3, or 3 minus that. That's gonna be a vertical shift upward by 3. Vertical shift up. Do you guys understand this play by play that I'm doing here? -infinity to infinity. The range. Now the range. What happens to the range? The range went from -infinity to 0, so the range is not going to be moved up by 3. So that's going to be -infinity to +3, but not including 3. 3 is now my new. My horizontal asymptote was y equals 0, but I shifted everything up by 3, so I had to add that by 3. So my horizontal asymptote will be what? Y equals 3. So this is the information that I need. And then this is the new horizontal asymptote, and then I have this as my graph of my function h, right? It's h, yeah. H of x. And this is what? Part B, and part C was what? Part C was asymptote. I got the asymptote already. So the asymptote here is part C, and then part D was the domain and range, right? So I got part C and part D at the same time. Okay, so here we are. Voila. So any questions about this? Is this clear? The sequences of transformations, the parent function, the domain and range, or horizontal asymptote. Everything looks easy when you're explaining it. Okay, so I said this to one of my students yesterday. I teach somewhere else, and I was saying the following. Teaching mathematics is kind of paradoxical. Why is that? Because exactly right, Chen. That's exactly right. That's the reality, right? When you see an instructor go over stuff, you're like, oh, so in a way, I feel like teaching mathematics is paradoxical in the fact that I'm showing you how to do something, but I'm showing you how to do something from perspective of it's not as hard as it seems. But on your perspective as a student, you're looking at this, and most of you maybe for the first time, and then you're like, oh, this is hard. But the way I present it gives off the feeling that this is supposed to be easy, but it's not. Mathematics is hard. Anybody that does mathematics for a living it feels like this is hard every time. It's easy. For example, this stuff may seem easy for us now. It's because we've been doing this for, I don't know, for like eons, like just so much. So it just becomes ingrained in us, right? With just like any other profession, any other skill, any other trade, if you do it for years, it just becomes part of it. Like it's easy in a way. But mathematics, learning mathematics in itself is hard every time. It's never easy. Especially when it's new stuff you've never seen before, it's always hard. So, when I do little mistakes here and there, I don't mind because I actually want to show you that it is part of the trade. It is part of the trade to make mistakes. It's part of it. And it seems as though it's supposed to be perfect, but it's not. At the end, we make it nice and perfect and clean but really mathematics is not. It's messy. It can be like a little like where am I going with it, you know? But anyways, the reason why it's not easy right now is because you haven't done enough. When you do enough and you know what that number is for you, everybody has a different number for enough. Oh, I've done enough of this because I already got this down pat because I've done a million of these, you know? But anyways, anything else? Compound interest, yeah. So we got two here. Um, so there's two. So there's compound interest of this kind, and there's also another compound interest problem, if I'm not mistaken, of these kinds. So which ones? These are different. So these here, the ones that you have original, the first ones, the first batch of compound interest is straight. Use the formula and plug in numbers into your calculator. These two here, on the other hand, are the ones where you have to solve for t, which require using logs. And the other one, you don't need logs. You just use the formula. So which one of those do you want? Do you want the ones that you need to solve for t or for time? Okay, so we're gonna do one of these. All right, that's fine. So let's look at this. Unless you want to do number two. I don't know. Up to you. Right. I'll go with number one. All right, so if we look at number one for compound interest, so compound interest. So what does compound interest number one say? It says that we have find the time that it takes an investment to grow from 5,000 to 8,000 at an interest rate of 7.5% per year compounded quarterly. Okay, so this reminds me of using the formula for compound interest, which is A times P, 1 plus R over N to the NT. What does P represent? P represents the initial amount, 5,000. What does A represent? A represents the end of this interest, the end of the growth of my investment. So my investment grows to 5,000. What does R represent? R represents the percentage, right? And what is the percentage here? 7.5%, which really is what? 0.075 as a decimal. What does N represent? Pardon me. It represents the number of times that the interest is compounded per year, which is four times. And what does T represent? T is what you're trying to figure out. T is missing. T is a variable, and T is in the exponent, so we have to use logs eventually. So for now, I'm going to plug in everything. I got 8,000 equals 5,000, 1 plus 0.075 over 4 raised to the 4t. So this is my equation. I have a exponential equation now. You see that? And my goal is to do what? Solve for t. Okay, so I need to do everything in my power that I can to solve for t. So this becomes what? When I divide by 5,000, divide by 5,000, the 5,000s here cancel. The zeros here cancel. And I'm left with 8/5 is equal to, and then I need a calculator for this. 1 plus 0.075 divided by 4. And I get, for my base, I get 1.01875 raised to the 4t. You see that? Now, what do I have to apply on both sides of the equation so that I can figure out what that t value is as an exponent? I don't want the variable to be an exponent anymore. So what must I do? I must apply what on both sides? I must apply logs. What kind of log? Any one. Just use one. So using log base 10 is okay, right? And then I get log on the left side 8/5. Leave that as 8/5 for now. And then what happens with this 4t now? I can place it out in front. I'm left with 4 times t times log of 1.01875. I still want to get t though. I need to get t by itself. So what must I do? Divide by what? 4 times log of 1.01875. And divide that also on the other side. 4 times log of 1.01875. What happens here? The 4's cancel, boom. The logs cancel, boom. And then I get t. T is equal to, this is the exact value, log of 8 over 5 all over 4 times log of 1.01875. And does anybody have, can anybody do this calculation for me? This calculator here that I have apparently doesn't have logs for a very strange reason. I don't know why. So does anybody have a numerical answer for this? 6.3. So this is 6.3252 dot 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 dot. So I'll trust you, Felipe, for this. Again, I'll upload the answers to all of these, for each of these later today. So you should be able to compare your answers. But I don't have it at the top of my head right now. So yeah, Great, great, great. So you guys got the same answer? Same. Good. So then how long does it take? It takes roughly approximately what? 6.3 years. So approximately 6.3 years. It takes approximately 6.3 years for $5,000 to grow to $8,000. Okay. All right. That's compound interest for you. That's how you use logs to figure out time. Anything else? We got about 10 to 35, right? We have about 25 minutes left. So anything else? Evaluating logarithms. Okay, so evaluating logarithms. Yeah, evaluating logarithms, number 2. Okay. Okay, so there's a lot going on in here, right? Okay, so first of all, you can rewrite log of the thing inside. So first of all, remember 5 and 125, how are they related? 125 is really what? 5 cubed. So look what I can do with this. This becomes log base 5 of what? Sorry, not negative, of 125 to the negative 1 power, because 1 over 125, right? I can rewrite that as 125 to the negative 1. Now, what I'm going to do is I'm going to put this negative 1, I'm put it in front. But negative 1 times negative a half is what? Positive. So this becomes what? 1/2 times log base 5 of 125. But I just mentioned that 125 is 5 cubed. So I can write this as 1/2 log base 5 of 5 cubed. But then what is log base 5 of 5 cubed? Well, remember that formula, that rule, log of any base and base raised to that x power equals x. That's one of the properties of log. We discussed that a few lectures ago. So log base 5 of 5 cubed is 3. So we got 1/2 times 3, which is really just 3/2, or 1.5. So that's how you evaluate number 2. Number 1 is 27. That's right. It is. Because remember, it's one of those properties of logs. If you have 5 raised to the log of base 5 of 27, they cancel out. 5 and log base 5 cancel each other out. So the answer here is also 27. That's a quick one. Yeah, so log base 3 of 16, that one, 3 and 16 are not connected to one another. So this is when you have to use a calculator for this one. And if you don't have log base 3, remember you can use the change of base formula and use any log. So this could be written as log of 16 over log of 3. For example, change of base. And then when you put it in your calculator, you should get the answer. So for this one, you would need a calculator. For 1 and 2, you don't. Yeah. All you have to do is divide log 16 divided by log 3. And then you get your answer. Okay, anything else?
Can we go over the degrees to radian and then one of the radians to degree?
Okay, well, we've done that one. We've done radians to degrees earlier, but we could do another one if you like. And we've done coterminal angles, but we haven't done degrees to radians. So let's look at that. So degrees to radians. Do you have a preference?
We could negative 315.
Okay, negative 315, right? So I wanna go from degrees to radians. So what must I multiply by? I must multiply by pi over 180. That's all I have to do. And then I get what? I get negative 315 pi over 180. Now what I can do though is I can simplify this further. I can simplify this by seeing what factors do 315 and 180 have in common, and what number do both of them have in common as a factor. 15. Okay. So then 315 divided by 15 is what? So this would be what? Negative 21 if you divide by 15. And then if you divide 180 by 15, what do you get? You get 12, right? But then, what happens? Can I simplify this further? Yeah, you're right, Felipe. We could have used 45. If I divide this by what? If I divide this by 3, I get what? I get negative 7 pi. And if I divide 12 by 3, I get what? 4. So negative 315 is the same thing as saying negative 7 pi over 4. And that's it. Okay? So negative 315 degrees is equivalent to saying negative 7 pi over 4 radians. All right, what else? Chad, is that okay, Chad? Do you want to go over one more or no?
Yes, can we go over one more and then someone mentioned the applications modeling after?
Yeah. So which one? And degrees to radians or radians to degrees?
We could do another degrees to radians.
Okay. And which one?
Can we do a positive on 150? We'll do number one this time. Oh,
One
matter of fact, no, I'm sorry. Can we do 72?
72.
Yeah.
72, same idea. Multiply by pi over 180. I got 72 pi over 180. What can I simplify with? What can I simplify this with? Oh, so basically here is just, 12. Right, so 72 divided by 12 is going to be what? 7. So 7 pi. And then what's 180 divided by 12? Well, we just did that, kind of, right? Oh, yeah, pardon me. Sorry, pardon me. It's 6. Can't divide properly. So let me just write that again. 6 pi, right? If I divide by 12, and then 180 divided by 12 is? No, it is 7, right? Am I just... No, it is 6, pardon me. What am I doing? 12 times 5 is 60. And then 180 divided by 12 is 15. So then the answer will be 16 pi, 6 pi over 15. That's equivalent to 72 degrees. Oh, you can simplify further. Yes, you can. You can. What does that become? Right. You divide both by 2, you get 3 pi over 15. Yes. So simplify as much as possible. Really, you're just simplifying fractions. And yes. You see this? You see this, guys? I mess up too. It's 2 pi over 5, 15. So you divide by 3, you divide by 3. So make sure, let me just write that down, okay? So you divide here by 3, and you divide here by 12. And that's your final answer. Oh my goodness. Wow. Thanks, guys. 2 pi over 5. See, you guys do better than I do. Look at that. Already masters at converting radians, degrees to radians. You see that? This is great. This is great. Good. Okay, we're good with this now?
Yeah.
No?
No, yeah, we're good.
Oh, okay.
This is the applications modeling now.
Yeah, applications modeling. Let's do that. So that's all the way over here.
Yeah, I
And we
think
got
someone
2 good
answered
ones
number
here.
2.
Number 2?
Yeah.
Number 2. Okay, number 2. Number 2 is a nice problem. The ball that's thrown from a height of 5 feet above, and it's modeled by this function here. And what you should notice immediately is that this function is what? Quadratic. This is a quadratic modeling problem. X, always notice what X is. X is what? X is the distance in feet that the ball has traveled horizontally. That's how much it traveled horizontally. And what does the function give you? Oh, I should have specified this a bit more. So the function, given this, the distance that it traveled horizontally, the function gives you the height of the ball. So f of x gives you the height. I should have specified that. This gives you height. So given the distance that the ball has traveled horizontally, f of x gives you the height. So that's why we want to find what? We want to find the height, the maximum height, and we want to find the horizontal distance when the ball hits the ground. So this is really like a two-part question. So this is part A, and this is part B. So the maximum part, I'm gonna use a certain color for that. So the maximum is part A, and then the part B is to find the horizontal distance. Okay. All right. So this has to deal with what? Like we just discussed. It has to deal with quadratics. It's a quadratic function. And this quadratic function, if you notice, the a value, even though this a value is kind of quirky, right, as 32 over 20 squared. And of course, you can take 20 and square it, you get 400. And of course, you can further simplify that. But the whole point is that this is a negative number. It's a leading coefficient is negative, and it's an x squared term. So what do we know for sure, for a fact? For a fact is that my graph of this function is going to look something like this. That's what my graph is going to look like. So again, let me write this down. So this is f of x is equal to negative 32. So f of x is equal to negative 32 over 20 squared x squared plus x plus 5. This is x. This is y. So this, remember, represents the height of the ball. And x represents the horizontal distance traveled by the ball. Now, I want to find the maximum height. So I need to find what? Vertex. And then I want to find what's the horizontal distance that it travels to get back to what? This is when the height equals 0. When the height equals 0, that means that the ball hits the ground. Ball hits ground. So again, this is for part B, this is for part A. So I need to find the vertex. So for part A, find vertex of f of x. Does anybody remember how to do that? I know this might be a while ago. But how do you find a vertex? Negative b over a, that's called the what? Axis of symmetry. That's right. The axis of symmetry is the first step. It's negative b over a. X equals negative b over a. Now, first I have to highlight what's my a, what's my b, what's my c. So then what's my a? My a is negative 32 over 20 squared. What's my b? My b is 1. What's my c? My c is 5. So what is my b? Negative 1. And what's my a? Negative 32 over 20 squared. What's a negative divided by a negative? A positive. What's 1 divided by a fraction? Keep, change, flip. So you get what? 20 squared over 32. And now from here, I can use your calculator for this. 20 squared is 400. And 400 over 32, what does that give you? What do you get when you get 400 over 32? You get 12.5. So my axis of symmetry happens to be here, what? Right here. But does that give me 12.5? Does that give me the maximum height? It doesn't. Remember the x value, what does the x values indicate? It tells me the horizontal distance traveled by the ball. So if my ball travels 12.5, I think what's the units? Feet. Yeah, this is 12 feet. Okay, I should write that down. This is height in feet. So the units is feet. The units is feet. So if my ball travels 12.5 feet forward, horizontally speaking, then it reaches a maximum height. And that maximum height we had to figure out by doing what? By plugging in. So what's the maximum height? What is the maximum? The maximum value of f is when I plug in the x value. So 12.5, when I plug that into my function, I get what? Negative 32 over 20 squared times 12.5 squared plus 12.5 plus 5. Now, what happens when I plug that in? What do you guys get when you plug that in? You get 5. The maximum height is 5 feet. It just so happens to be 5. It's not because there's a 5 here. So don't think that because it's a 5 there. Um, uh, so that's a problem. Maybe the problem that it can't be 5 because it starts out at 5. So that's kind of peculiar. Hold on, 20 squared. 20 squared is, let me just write that down. 20 squared. I don't think there's a problem. It shouldn't be a problem question. Hold on. Let me see if I can graph this. So this is what? Negative, what was it? 32 divided by 400, right? and then I multiply that by x squared, and then I add that by x, and then I add that by 5. You see this? So there's something wrong with the calculations. Um, it starts at 5, which makes sense, but then this height here is 6.25. So there's something wrong with the calculation. So let's go back. So what may have gone wrong here? B over A, right? That's negative B over A. That's the axis symmetry. And the A is 20 squared. And then I get this though. I get my axis symmetry to be 6.25. Oh, guys. You guys gave me the wrong. Well, okay, I should have noticed that myself, but the axis symmetry is not negative B over A. It's negative B over 2A. It's negative B over 2A, guys. Please be careful with this. Please. It's negative B over 2A. Okay? No, it's fine, Chen. No, I should have noticed. I just went with it because negative B over A is another expression related to quadratics, which is the sum of the roots. So then I just thought that was it. No, but the axis symmetry has a 2 in the denominator. Because of that, then our answer will be, this will be multiplied by 2, right? This will be multiplied by 2. And yeah. And then when you multiply this by 2, you're having this. So when you have this, you get 6.25, which is exactly what it's supposed to be. And then when you put 6.25 instead, what do you guys get instead if you put 6.25? 6.25 instead of 12.5. You don't get 5 because it can't be 5. You start out at 5. And when you plug in 6.25 instead, what do you get? 8.125. That's right. Now we're talking. Now the height here is 8.125. So that's the coordinates of this vertex. It's 6.25 comma 8.125. Okay, and then we say what? We say that we can conclude everything by saying the ball reaches a maximum height of 8.125 feet, 5 feet. So this is not right. Of 8.125 feet when it has traveled a horizontal distance of 6.25 feet. Okay? Okay, that's part A, and then we have time to finish part B. So part B asks for what? If part B asks for the horizontal distance when the ball hits the ground again. So if the ball hits the ground, that means that the height equals 0. And what models the height? That f of x models the height. So essentially what you're going to be doing is solving the quadratic equation. So my quadratic is again what? Negative 32 over, I'm just going to write 400 now, x squared plus x plus 5. That equals 0. Obviously, this is a pretty, you can't factor this quadratic equation, at least not to my knowledge at the moment. So then you would have to use quadratic formula for this. You use your graphing calculator as well. But then so we already specify where A, B, and C is. And whoops. Sorry about that. And then the quadratic formula states the following. So x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. This will be what? Negative 1 plus or minus the square root of 1 squared minus 4 times negative 32 over 400 times 5. All over 2 times a, which a is what? Negative 32 over 400. And might as well just, you can write what's 32 over 400. So 32 divided by 400 is 0.08. So you just write all of that as 0.08. So negative 1 plus or minus the square root of 1 squared minus 4 times 0.08 times 5 all over 2 times negative. Again, this is negative 0.08. So if you put that in your calculator, you should get a number. And of course, we're going to use not the negative one, because the negative one is the one that's here. This is the negative. I want the positive one. So the positive one is when you use the plus. I don't know why it goes all the way down. When you use the positive one, so you see the plus and the minus. So we're not going to use the minus, we're going to use the plus because that's the one we care about. So we're going to use negative 1 plus the square root. Let me just see if I can get that real quick. So we got 4 times 0.08 times 5 plus 1. So you guys get 2.6 for this? 2.6 in the bottom here. And then this is 2 times 0.08 and 0.16, negative 0.16. And so you get, we're going to use the negative one because we're going to use the negative one because that will give us a positive at the end. So this will be minus negative 1 minus the square root of 2.6. And then we divide that by negative, let me just show you, by negative 0.16. And I get 16.327. And let me just confirm with this guy here. Negative 16.327. That's right. So see, the root here is 16.327. So you can use the graphing calculator to figure out what that root is, or you can use the quadratic formula for that, and you get the same thing. You get 16.327. So then what's the final answer here? We're trying to figure out the total horizontal distance traveled when the ball hits the ground. So the ball travels a horizontal distance of 16.327 feet when it hits the ground. All right. Any questions about this? Everything okay with this? Why didn't we add? Okay, so very good question, Prab. You can try it yourself. If you add, look what happens. What do you get? You get negative 1, right? So negative 1 plus the square root of 2.6, I get 0.6, right? And then if I divide it by negative 0.16, I get negative 3.8. You see that? I get negative 3.8. So we get this one. Remember, I just mentioned it. We get the negative one. This is negative 3.8. That's if we add it and divide by a negative number. We get a negative value. But I want a positive value. And the only one that gives me the positive value is the one where I have a negative in the numerator because the denominator is also negative. So negative divided by negative becomes a positive. That's why I get to positive 16. Okay. All right.